So yeah, I'm John Brandt, and for about 25 years now I've been building tools to refactor code or migrate code, transform code. I started out building tools in Smalltalk for refactoring Smalltalk, then I went to migrating Smalltalk using the same tools, and now I migrate pretty much any code to other code. So there's many ways to migrate code, and this is kind of my strategy. So first thing, you have to define the parser for whatever language you're going to migrate from. A lot of times we already have the parser, but sometimes you don't. So you define the parser. The next thing is you create your transformation program. That's going to basically run and convert all your code to the new language. And one of the final things is a lot of times we'll have to have a compatibility layer, because there's features in the old language that aren't available in the new language, and we'll need to support those. Now, SmaCC itself just handles the first two. The compatibility layer is all up to you, but SmaCC can help you both on the first two. And the good thing about this migration strategy is that essentially the developers can continue their normal development using the old system. So it really reduces risk. As long, they can develop, I can go in and define the rules, do all that work, and so you're not stopping development. If I fail, all it is I didn't, they can still use the old system. The bad part about this, and the reason why most people don't like these migrations, is it keeps the same design. So if you had a poor program before, you'll still have a poor program after. This strategy works fairly well for probably 100,000 line programs and up. Anything smaller than that, you're probably getting into overhead that you might just rewrite it by hand or use some other method. Most of the projects I've done have been in the range of 1 million lines. I've done probably from 100,000 up to 6 million or so. So SmaCC itself is basically just a standard parser generator, kind of like along the lines of Yak or Bison or something like that. It's an LR parser generator, an LR1 parser generator. It supports the GLR, or the generalized LR, so it can do ambiguous grammars. It can also generate ASTs, and it does some pattern matching. So here's a basic grammar for a simple expression. I guess it's just just simple addition, where you can have a number plus a number, you can put parentheses around it. Now all the code, if you remove out all the underlying code, that's just the grammar for that. The underlying code is for defining the AST. So you can see, the first thing is that percent root expression. Essentially that defines the root of the hierarchy for your AST nodes. Suffix is basically the suffix we're going to put on all the nodes. So then in each one of those we can define a variable. So if we have on the first line an expression, or the first production expression, it says we're going to have, for that addition expression, that we'll have a left variable that holds the left expression, the operator variable, which will hold the operator token, which will be just the plus. Then we'll have the right variable, which will hold the right expression, and we'll create a binary node for that. Similarly, like the second line, we have a left paren and right paren. However, we do not name the expression in that line. In that case, SmaCC will figure out that what you're really wanting to do is add the left paren and right paren to whatever that expression returned. And since it sees that the type of that node is going to be an expression, it can actually figure out that what you want is a collection of variables with the left parens, a collection of left parens and a collection of right parens on each expression node. So from that grammar, we generate essentially these three classes. with expression node being the root. We have our left parens being a collection of parentheses, or a collection of parentheses tokens, right parens being a collection of the right parentheses tokens. And all nodes will have that. Our binary node will have our left and right with the operator, and the number node will have the value. Now, the transformation program is really where all the work really takes place in the project, because there's where you're writing your rules to convert everything. And for the SMAC, it has basically a set of rules. It's or not a set, more. It's an ordered list of rules applied in order, and you can define some methods and properties that you can use in those rules. So there are essentially two different types of the rules. There's the declarative pattern rules, and there's the imperative coding rules. Imperative coding rules basically gives you small talk. You can write whatever you want. It doesn't even have to do anything per the migration. You can write stuff that loads files or whatever. It just lets you do about anything. Generally, those type of rules we use for generic or general syntax. So if you're converting a method or a class, this is the one that will convert all the syntax for the method or class, a lot of times in those imperative rules. And they can also do some control flow. So if you want to process one section of the AST before another section of the AST, that's what they handled. Now the pattern rules, a lot of times we use those for things that are one-off. So you're in the middle of a file, and you notice this one expression needs to be treated differently than every place else you've had that expression. There might be something special in the context. So you can write a pattern rule just for that one location. And the good thing about those are they're fairly quick to write because they look exactly like the code, and you can transform them that way. So in the pattern rules, essentially the search expression is just a normal text string like you would have from your program, except that you have these patterns in the middle of them. And on the search part, it gets parsed into an AST. On the replace side, the whole pattern is just a string that gets macro expanded. In order to support pattern matching in our parser, we have to define first that it needs to be a GLR parser, because what we do is every place you have the pattern in there, we have to parse all possible trees with that pattern in there. So the pattern could, on our example here, the pattern could match a binary node maybe, or a pattern could match a number node. We might have to parse, all possible interpretations of that. So we need the GLR parser. We also need the pattern token. Since, various languages have different grammars, we need to have something that's does not conflict with the existing grammar. So I know most languages do not use a back quote, and so that's what we normally use. So here we have a pattern token is going to be a back quote followed by anything that's not a back quote ended with a back quote. There's languages like JavaScript now that's using back quote, so you might have to do something different for those type of languages, and that allows you to specify all you want. So using that, we can write then expressions like the one you see there, where you have a plus a, or the pattern variable a plus the pattern variable a is going to be rewritten by whatever the pattern variable was, a times 2. And basically that pattern variable can match any AST node. So it can match a single number, it can match a binary expression. So here's our example, or an example. We have original code of 3 plus 3, and we're going to search for the pattern a plus a. So what we do is we parse both of those. So on the left we get the standard AST. And on the right we get an AST but with the pattern variables in there. So we have the anything node in there. And we run unification across that, and we get the pattern variable a equals 3. Now, if we had 3 plus 4, we'd run unification. Unification would fail, and so it wouldn't match. Now, whenever we have replacement works a little bit differently. It's not, we don't parse the expression, we treat it as a string macro. Instead, what we do is whatever got matched, we just delete that and replace it with whatever that string macro expanded out to. I think this works fairly well whenever you're converting from one language to another. Otherwise, you'd end up with 2 different parse trees from 2 different languages or in the same tree, essentially, or 2 different parse nodes from different languages. So that's the reason why on the rewrite, we don't rewrite trees, we rewrite with strings. So essentially take the string, delete it, take the replacement macro or the pattern macro, put in the whenever we have the pattern variable in there, we process that subtree, and whatever it returns, we put that in the macro and replace that. So in our example, we had the replacement. We wanted the pattern variable a times 2, and we matched with the pattern variable a equal 3, so replace everything with 3 times 2. So here's a couple of examples from some migration, some Delphi code that we did. The first one is one of these kind of one-off expressions. You go through and you start to migrate the code, and you notice that, some places they use this for loop, which the ending condition was -1. The normal for loop rewrite would have been less than or equal to C -1, but we could change that to be less than and make the code a little bit nicer. So that's the type of one-off expressions that we'll do in the pattern matching to make the code a little bit nicer whenever it's converted. The second one is actually some code that in .NET, you're not able to set the minimum size or the minimum height of a window by itself. You have to set the minimum size, which includes the height and the width. So what we do is whenever on that a/forms t custom form, what that's essentially saying is we're going to match something, we'll call it a, but it has to be of type t custom form. So if you're doing it from some other thing, it's not going to match. So the type of whatever a is has to be a t custom form. So then the code rules. So code rules in SMAC are essentially just any Smalltalk expression. For the search part, what we do is we have an AST node that must match, then some code that returns, if it returns true, then it's going to match. The replacement are generally either in 3 different forms. So they're like edit expressions, so you can edit the methods or edit the source code. Control flow, where you tell it which nodes to do, or just generic Smalltalk code where you can load files, do whatever you want. Edit expressions. So we tried to make it so that create a language so that it looked more like what you would think of whenever you're describing what you're wanting to do. So you do things like self-replace some node with some text for replacing, if you want to move one node before another, you can do self-move this node before another node. So we try to make it like what you would think if you were editing what you would tell somebody to do if they were sitting down at an editor. Same with inserting, deleting. Control flow. Normally, the way SMAC handles stuff is it starts from the root of the tree and processes down until it finds a match. And on these code rules, once it finds a match, unless you tell it to do something, it's going to stop right there. We can change that by telling it to either, you can process the children of this node. You can continue on processing this node. So if some other later rule matches the same node, You can process whatever. So like if you wanted to process the tree bottom up instead, all you'd have to do is write a rule that said self-process children, self-continue. And that would change from a top down to a bottom up traversal. So here's a couple of examples of those type of matches. First one's from Delphi, where we just take a statement block, has a begin and end, and we do replace the begin with a opening curly bracket, replace the end with the ending curly bracket, and we continue process the rest of that tree. The second one's from some Power Builder migration, where we migrated to C#, and they have these function objects, and in the function object we need to check whether we check the type node, but the type nodes can be any type of Power Builder type. So we also need to check whether it equals function object. So, and whenever we do that, we set a couple of properties. Then we just replace the whole match with a partial beginning of a partial class. So that's pretty much it for the type of rules that we can do in SMAC. One of the things I have done though is to add some custom tools in there. So here's for a custom debugger that we have for debugging grammars. So if you debug your parser, one of the things, if you have a table generated parser, a lot of things are just like numbers in your table. So it's really hard to debug. What we do is we store off kind of the meaning of those tables, or the integers, and give it symbolic names. So here we have our parsing some JavaScript code, and in the top left we have our stack of what's being parsed. So at the bottom level we're parsing you got the module list, then we have the var token, and then the variable declarations and the comma right before that. So we're right at parsing. Let's see if I can read that there. I can't. Too small. But we're parsing what's selected there in the bottom, or in the middle. And that's our look ahead. So in the top right here, we have essentially all our possible actions for that look ahead, or for that state that we're currently in. And so we can, if you could read, it's going to match this identifier, and it's going to do a shift action. So the next thing we're going to do is shift that identifier. A lot of times what will happen is if you have a parser error, you can open up the debugger and you can see immediately, oh, we have this type of token, and there's no action for that token, and that's the error. So you can see immediately you should have had an action, so you might have missed a semicolon or whatever earlier on. So that's the type of stuff we're going to look for. The GLR will just list all the states. So if it's doing multiple parses in the grammar, we can see that it's actually ambiguous grammar, so we have multiple different paths through there. So we have the section here which shows the input that we're parsing. You can actually select someplace in the middle of the input and do step the cursor, and it will parse to that location. The scanner state is here. Normally, unless you're, it will always display like the scope. So the SMAC parsers can have multiple scopes that it's scanning in. And if you're in the middle of scanning it, shows some more detail. And the bottom's the standard debugger information that you would see. Normally, it's not that interesting. So when we match, we also have preview support. So you run a rule, say preview, and it'll bring up two different windows like this, or two different views with the input on the left and your resulting code on the right. What you can do is put your cursor anywhere in there. You can select some stuff. So here what I did was like put the cursor like in here. And when I do that, it tells me which rules change that piece of code. And if you select a rule, it will then highlight the sections on the right of every little piece of change. So here, I selected here for this, and it told me this event declaration node rule changed that text. It put in this piece, added the semicolon there, and added the ending parenthesis. On the left, it just highlights the node that actually matched. Now from this, I could actually tell it to go to the rule directly from here. I can also tell it to bring up the debugger. So I have a rule debugger, which has essentially the stack of the rules up there on the top left, the rule that's being executed. We have the original code and the ending code. And we can step through there. We can also scroll down here and run the cursor or whatever. This down here is just some inspector stuff. So with all these tools, it makes it a lot easier to get to where you need to be for finding out who changed this and why, when it's not performing correctly. So with that, I'll open it up for questions. Yes?
When you parse the patterns, you mentioned you had to have a GLR parser to parse them. So do you have a way of like starting the parser such that it's not necessarily looking for the start rule of the grammar, it's looking for...
Yeah, because basically what he's asking is that how do I start from any place in the grammar, and because you can't just start from the start node, because these patterns can be any node down below, and the way I do it is start from all of them, and most of them will fail immediately because they won't be able to shift what you're looking for, and the patterns are fairly small. It's milliseconds essentially to. Yeah. Yes?
How do you resolve conflicts between overlapping patterns?
So how do I resolve conflicts between the overlapping patterns? What I do is actually take all the possible patterns. So I will, if this pattern expression can potentially be, 5 different subtrees, I'll try them all for matching. Any other questions? Okay.